In Chapter 3, we introduced valence bond theory as a technically incorrect but helpful way of simplifying molecular orbital theory. Valence bond theory and molecular orbital theory are also helpful ways of understanding reaction mechanisms, which we'll see in this chapter. First, let's recall that molecular orbital theory predicts not just the stabilized bonding orbitals, but it also predicts the destabilized antibonding orbitals. We also introduced the concept of a HOMO, which is the orbital most likely to donate electrons, the highest occupied molecular orbital, and the concept of the lowest unoccupied molecular orbital, the LUMO, which is the most likely to accept electrons. Identifying these orbitals can help us to predict reactivity, since HOMOs of one molecule tend to interact with LUMOs of another. Frontier molecular orbital theory states exactly that. For a reaction to occur, we will proceed through an intermediate where the orbitals with the highest and lowest energy, the frontier orbitals, the HOMO and the LUMO, will interact and stabilize a transition state. The transition state is stabilized in both directions of the reaction, which is a principle we call microscopic reversibility. Stabilization occurs similarly to the way that orbitals mix. You need constructive interference for it to happen. Differences in symmetry between the sigma orbital and the pi star orbital shown here mean that there will be no net interaction and therefore no stabilization. On the other hand, if the pi orbital interacts with the sigma star orbital, as shown, now stabilization can occur because the pi electrons can overlap beneficially with the sigma star vacancies. Notice also that the shape of this overlap will determine the type of bond formed. In this case, the structure at the right will form a sigma bond because of sigma overlap. Let's think about the mechanisms that we talked about in Chapter 7 through the lens of frontier molecular orbitals. In a proton transfer reaction, electrons are donated by the base and received by the acidic proton. Notice that the electron donor is then the HOMO. The highest occupied molecular orbital is going to be the one that has the high energy electrons to spare. This feeds into the sigma star antibonding orbital from hydrogen and chlorine, forcing the chlorine out with an antibond as the new bond is formed. Notice also that this reaction needs to happen when the HOMO coming in from the opposite side of the chlorine. It cannot happen with the HOMO coming in on top, for example. A bimolecular nucleophilic substitution step is nearly identical. An electron donor kicks out a stable anion in a single step. The frontier molecular orbital description is therefore also identical. The nucleophilic HOMO is stabilized by the LUMO, which is the leaving group antibonding orbital. Coordination steps involve a LUMO that is often an unoccupied atomic orbital. In organic chemistry, usually it's a p orbital. The HOMO in a coordination step could align with either side of the p orbital, meaning that for some molecules, two enantiomers could form. Because of the principles of microscopic reversibility, heterolysis, the opposite of coordination, will form an empty p orbital, but it doesn't matter on what side the leaving group leaves. Bimolecular elimination, like bimolecular substitution, involves two separate molecules interacting in specific orientations. However, it actually involves two separate HOMO-LUMO pairings. Let's first look at the HOMO from the base with the LUMO from a CH bond. Pairing between the HOMO and LUMO in this case forces electron density into the sigma star orbital, accumulating on the opposite side of the CH bond. So pin that. Normally, a carbon-hydrogen bond isn't particularly acidic, except for that in this case, the HOMO-LUMO interaction can occur between a filled carbon-hydrogen sigma bond and an empty sigma star carbon-bromine antibond. This overlap allows the bromine to start leaving and the hydrogen to be way more acidic. This only happens appreciably though when the HOMO and LUMO line up, which is always going to be in the anti-conformation. It doesn't happen in the syn conformation at all because the HOMO and LUMO are far apart. Nucleophilic addition steps involve a nucleophile HOMO to stabilize a pi star antibonding orbital, like we see here. This must happen from above or below the double bond to match the orbital symmetries. So we have to have the new lone pair of electrons coming in from above or below the carbon's antibonding orbital. By the principle of microscopic reversibility, nucleophilic eliminations are the exact reverse. A HOMO from one of the atoms stabilizes a sigma star antibonding orbital to kick out a group. Electrophilic addition will take pi electrons as the HOMO and interact them with an antibonding orbital to pick up a mostly positive piece, often from something else, which we can see here. And by microscopic reversibility, that same new sigma bond can be removed to form a pi bond. Perhaps the most useful addition of molecular orbital theory to these mechanisms is the description of hyperconjugation. Carbocations can be stabilized by interactions of adjacent sigma bonding orbitals with an empty p orbital. But because these orbitals are already interacting, a new sigma bond begins to form with the carbocation. As the H bonding orbital loses bonding character to the original carbon, other sigma orbitals can in turn stabilize the newly forming empty p orbital, helping the hydride or alkyl groups to walk along the molecule to form the most stable carbocation. These types of molecular orbital descriptions can be sometimes redundant with the reaction mechanisms, but they offer valuable insights into some reactions and why they happen the way that they do.